Hi, thanks everyone. This talk is going to be shorter and lighter than the KKL linear theorem and the Friedgut's Junta theorem. Let's start slow. Let's just recall a theorem so that we all of us are on the same page. We're working with Boolean functions, so let's start with the hypercube. We're working Boolean functions over the n-dimensional hypercube. And what's our definition of influence? Our definition of influence is we pick a random x and you check the probability that flipping the ith bit changes the value of the function, right? So fx is not the same as x with the ith bit flipped. All right, and just to visualize it, it'll be nice to keep in mind a picture of the hypercube and the function as a labeling of each of the vertices of the hypercube with a 0, 1 value. Great. So what's the KKL linear theorem? Let me motivate it a little. You will all throughout the talk we'll talk about balanced functions. So the function takes value 1 with probability half and 0 with probability half. And the simplest such function is a dictator function. You just pick the jth coordinate and output the value of the coordinate. And so the quantity we'll look at are the influences of such a function. So for the dictator function, we know, let's say the jth dictator function, you know that the jth influence will be 1. Flipping the jth bit will change the value by 1 and everything else will not affect the function. So some of the influences of a dictator function is 1. And here's an easy fact by some simple Fourier analysis that for any balanced function, the sum of the influences must be at least 1. In particular, this implies for any balanced Boolean function, we'll get a coordinate that has influence at least 1 over n. But the KKL linear theorem says that in fact this something even stronger is true, and for any Boolean function, there will exist a coordinate. So I'm assuming Boolean and balance. So there exists a coordinate such that the influence is at least log n over n. It might seem like a small improvement over 1 over n, but this is it's very significant in all the applications of this theorem. The second theorem we are going to study is a Friedgut Junta theorem. Here's another simple Fourier analytic fact. So let's say you have a balanced Boolean function which satisfies the equality that the sum over the influences is exactly 1. It's not difficult to show that the only such functions are either dictators or anti-dictators. So there must be a j such that fx is either xj or 1 minus xj. And so it depends only on one coordinate. How about if I tell you that the sum of the influences is not exactly 1, but it's small? What can you say about the function now? And Friedgut's theorem says that in fact every Boolean function is epsilon close to another Boolean function which only depends on few coordinates. So let's clarify again. So epsilon close means that the probability that you differ is only epsilon over a random x, and the number of coordinates you depend on is independent of n. That's the most crucial point in the theorem. There's an exponential dependence in the total influence and 1 over epsilon. That'll be largely of no concern for us. Just that it's constant, given constant total influence, right? So this talk is going to be about generalizations of these theorems. In order to get a flavor of what a generalization really means, I think. Sorry.
Every Boolean f is.
So no. So it goes into the number of coordinates, right?
Oh, wait, what is
so I is the sum of the influences, right? So if the sum of the influences is large, then you get many more variables. Right, so both these theorems are over the hypercube, and over the hypercube, influence can have several different interpretations. Let's quickly go over these interpretations because these will help us in order to study the various ways these theorems can be generalized. Right, so here's the definition we started with, that the influence of the ith coordinate is the probability that for a random x, you can flip the value of the function by flipping the ith bit. right? So you just focus on edges that go along the ith coordinate, the edges that are highlighted in green here, and I'll just rewrite it as so the influence can be rewritten as, you pick a random x, you look at the edge x and x with the ith bit flipped, and what's the probability that the function is non-constant over this edge, right? I've not done anything, I've just rephrased. So let's see another equivalent definition. You pick a random x, and over the edge x and x with the ith bit flipped, you compute the variance of the function in the ith direction, right? So I'm being sloppy with constant factors here, but up to constant factors, this is another equivalent definition, right? For a few other definitions and generalizations, it's useful to think of, since f is a Boolean function, I can identify it with the set of vertices, a set of vertices being where the function takes value 1. Right, and then I can look at influence as the fraction of edges cut in the ith direction. So, for example, here the edges, the red edges go from the set fx equals 1 to fx equals 0, right? And so when you measure edges in the discrete sense, in a continuous sense, you can think of it as the fractional size of the boundary in the ith direction. So it will be useful to keep these different definitions of influence in mind, because when we survey what kind of generalizations there are of these two theorems. Okay, so let's see the generalizations. I'm going to do a quick survey. It's not really complete, but I'll touch upon the most relevant and in some sense easier to explain generalizations. So what do I mean by generalization? I don't necessarily mean that it implies the KKL theorem, but I mean theorems of the following form. So you pick a Boolean function over any domain raised to n. So you pick an n tuple of values from this domain, and you want to claim that for any such Boolean function there must exist a coordinate which has influence at least log n over n. Right, we'll study theorems of these kind. So let me survey the various kinds of theorems that we improved in this sense. So one easy generalization of the KKL theorem is that instead of picking the uniform distribution over the hypercube, you pick a p-bias distribution over the hypercube, and the influence continues to be defined as a probability over a random x that the value does not flip. Okay, another generalization that follows from a very similar proof is, in fact, instead of the hypercube, now let's say your domain is a finite probability domain. So let's say values 1, 2, 3, and you randomly, each coordinate is a random value amongst 1, 2, 3. But the right generalization of influence here is that you look at the variance definition. So you pick a random x and you look at the variance along the ith coordinate of the function. Right? So that's another case where this is true. In the continuous case, there's a result by Boolean et al. Where it says, now you look at the function where the domain is the continuous interval 0, 1. Okay, and we'll use the definition of influence whether the function is non-constant along direction I. You have to worry about the measure of the set, and it must be, you have to worry that measure 0 sets must not make a difference, but let's ignore those issues for now. So, but for this definition, is the function f non-constant along direction I, you can prove a very similar theorem for the domain 0, 1. We'll largely be interested in the discrete case where so these were two results that were already known. There are a couple of other results in the discrete case. Oh, sorry. Let me recall another continuous result. This is a result by Keller, Mossel, and Sen. Now your domain is allowed to be a Gaussian, right? So you sample a real value with the Gaussian distribution, and the right definition of influence in this case is the measure of the boundary in the ith direction. There's a caveat that it's not log n by n, but root log n by n, but it's essentially a similar theorem. Okay, we are interested in the discrete case. The rest of the talk will be about the discrete case, and in some sense, the most general topological notion of a boundary in a discrete case is given by a graph, and that's what we'll talk about. So a domain will be the vertices of a graph. So each coordinate is a vertex from the graph, and a graph raised to the power n, we will study the Cartesian product, which I will define very soon. And the notion of influence will study the fraction of edges cut in the ith direction. Okay. I've hidden all constants that depend on the domain, just to be sure, just to keep things clean. Maybe I'll quickly say that there are some very nice generalizations that don't fit into this frame. Yes?
So what do you mean by fraction of edges cut direction? That for some random fixing of vertices on all but one coordinates,
yes.
On that coordinate you look at how much the size of the cut is.
Right.
So
but only measure the edges, it's not the variance definition.
And
right.
then of course this will be more interesting if the graph itself is of super constant size.
Exactly. Right, because otherwise you can go better. Yeah, so and I'll define these formally very soon. But I want to complete a quick survey that these are not the only kinds of theorems known. There are theorems known in the non-product setting. In fact, there's a very nice work by O'Donnell and Wimmer that gives such results for certain generalizations of Cayley graphs. And another result of Rosquin, I don't even know if I'm pronouncing the name right, and Ledoux, that encompasses several of these results and works for non-product settings. And the product settings, there are a few more definitions of influence too. So you see there's quite a long history, but we will focus on the discrete case with graphs. For the Junta theorem, there's a much shorter, cleaner history, and the generalization is similar. So you specify a domain, and you say that every Boolean function must be close to another Boolean function that depends only on few coordinates if the total influence is small. And I have to specify what's a definition of domain and the influence. So Friedgut in his original paper first proves it for the uniform distribution over the hypercube and then the p-bias distribution over the hypercube. And we show that in fact this notion generalizes to again where the domain is a graph and the influence is defined by the fraction of the edges cut. Okay, so the Junta theorem, both over the hypercube and graphs, in fact, has applications to hardness of approximation. So, all right. So let's cut to the chase. Let's define what is a concrete domain. So I have to define. So over the hypercube, it was for the original theorems, we knew the domain was hypercube. Now I have to define that if your domain is the graph, I have to define what's the n-fold product of the graph. So these are called Cartesian products. I will give you this definition more visually. So let me construct the hypercube in an easy way. So here's a way to construct the dimension 1 hypercube. That's just an edge. So you have two vertices, you connect them by an edge. For dimension 2, you have four vertices, 2 squared. You can draw edges along the first direction, and then you draw edges along the second direction. Similarly, you can construct a 3-dimensional hypercube. This definition generalizes to graphs. So let's see how. So here's an example of a graph over 4 vertices. So you pick 4 square, that's 16 vertices, and you first draw graphs along one direction. You pick a copy of the original graph along one direction, and you pick copies of the graph again along the second direction. Right? This is called a Cartesian product of a graph. You can extend this definition to undirected but weighted graphs, and that's equivalent to picking reversible Markov chains. But though we'll not focus on the Markov chain perspective here. So a little bit more formally, our vertices will be for an n-fold product of a graph. Our vertices will be n tuples of vertices, and I will draw an edge between two n tuples if exactly n minus 1 of them are identical, of the values are identical, and in one coordinate you have an edge, right? So you have all these vertices are identical, and then you have uv, where uv is an edge in the original graph. So that's the Cartesian product of a graph. Right? Any questions so far for the definition? So, so you see in a straightforward manner that an edge gives you a hypercube. If I pick a path, I get the grid. If I pick a cycle, I get the torus. Right? And so on. So our main tool, in fact, will be the log Sobolev inequality. Let me actually get back to this in a second. Let me state our results so that we are on the same page. So now we'll consider Boolean functions over the Cartesian product of n-fold Cartesian product of the graph, and we show that in fact there exists a coordinate such that the influence now the influence is defined as fraction of edges cut in the ith direction. Right now I guess the definition of influence is very clear, right? You fix everything, all the other vertices randomly, and along one vertex you vary one of the coordinates and measure the fraction of edges cut. Right? And there exists a coordinate with influence that is at least log n by n, and is a constant of the graph that's called the log Sobolev constant. We'll define that in a second, and we give a generalization of the Junta theorem. So for every Boolean function defined on the Cartesian product of graphs, it's epsilon close to another Boolean function, where you depend again only on few coordinates if the sum of the total influences is small. All right. So the dependence on the graph in both these results is based on something called a log Sobolev constant. Let's get to that next. So the log Sobolev constant appears in an isoperimetric inequality for the graph called the log Sobolev inequality. How many of you have seen the log Sobolev inequality? Okay, so that's about 60-70% of the. So let me motivate the inequality if some of you have not seen this before. So for any graph, for any function, we know the spectral gap inequality. It's a right. So if you look at the quadratic form over the graph, fx minus fy squared over a random edge, we know that it's at least lambda times the variance of the function, right? Where lambda is your spectral gap. Now the variance of the function in some sense measures how far f is from a constant function over the whole graph, right? We can use different measures, another measure in order to quantify how far f is from the constant function. One such measure is called the entropy, and that in fact will give us what's called the log Sobolev inequality. I'll define the entropy in a second. So the log Sobolev inequality says the quadratic form of a function f is lower bounded by the log Sobolev constant times the entropy of the function. Okay, and the entropy of a function is okay. So let's parse this. So you take the expectation of the function f squared log f squared, and you divide you subtract what you would expect if f was replaced by a constant function with the same expectation, right? So that's defined as the entropy. In some sense, we'll not really need much about the entropy. All you need to know is that it's a convex function of f, right? And it's always non-negative. As in fact, it's zero if and only if f is a constant function. Right, so here the constant involved in the inequality, the best constant is called the log Sobolev constant of the graph. So all of us essentially have seen hypercontractivity. Log Sobolev inequality is in fact a differential form of hypercontractivity, and there are reductions either way. Log Sobolev inequality implies a hypercontractive inequality for the operator e to the minus L, and the other way around. And another very nice fact is that in fact this inequality behaves very nicely under the Cartesian product. So given an inequality for the graph G, for the Cartesian n-fold Cartesian product, you get the same inequality, but now the constant becomes the constant over n. Alpha G over n is the new constant for the inequality. In fact, and it's a strict equality. Okay, so I already mentioned our results. So, and the log Sobolev constant is what is the only dependence on the graph when we state our generalizations for the KKL and the Friedgut Junta theorem. So the influence. So in the KKL theorem, you find a coordinate with influence log n by n, with a factor with the log Sobolev constant of the graph appearing here, and you lose the same factor when you bound the number of coordinates required to approximate the function with the Junta. Yes. In fact, it's fairly difficult. So bounds are known for quite a few families of graph, but exactly it's known for very, very few graphs. But for some operations, it's known to behave very nicely. And in particular, Cartesian product is one of the main operations where it behaves. But why is it of importance? In some sense, I think highlights. So, for example, you can use the spectral gap inequality in order to bound how quickly a Markov chain mixes over the graph, right? You can use the log Sobolev inequality to bound the same, and you get better bounds if you know the log Sobolev. In some cases, if you get better bounds. In particular, the dependence on the size of the domain is improved when you use the log Sobolev inequality. Okay. All right. So in the last 7 minutes, maybe I want to give you a quick idea of the proof. So Elkanan already talked about the method of martingale differences. Let me quickly define that. What does it mean here? So we are starting with a function on a Boolean function on the hypercube. Let's define these conditional expectations. So define G1 to be the average taken over the first coordinate, G2 to be the average of G1 over the second coordinate, and so on. And define. So here's how you construct G1. So this was our original function as a labeling. We average along the first coordinate to define G1, average along your second coordinate, third coordinate to define G2 and G3. And define the differences of these functions as fi. So f1 is defined as f minus G1, where G1 was the average along the first coordinate. F2 is defined as G1 minus G2, and so on. So these, so here's a concrete definition of fj. You take the average of f along coordinates x1 to xj, and you subtract the average for up to coordinates 1 from coordinates 1 to j minus 1, and these are called martingale increments for the function f. Right? We will apply the log Sobolev inequality to these functions, fj. So this is for the hypercube. What do we do for a general graph? For a general graph, all I need to the definition of the function remains the same. All I need to specify is how do you take the averages over the vertices, and it's the standard volume bias distribution over the vertices. So the probability of a vertex v is proportional to its degree in the graph. Okay, and if you are working with a reversible Markov chain, the probability is the probability distribution is the stationary distribution over the Markov chain. Okay, so this is so we've defined these functions that are the martingale increments fj, and sometimes I just want to show you that these functions behave very nicely. So here are some very nice, easy to verify properties. First is that they're all zero variance, right? This is incredibly simple. Two, in fact, importantly, is that they're orthogonal functions, where you define the inner product space to be according to the uniform distribution over the vertices. The uniform distribution over the hypercube, or the volume bias distribution over the vertices. And this in particular implies that if you square the L2 norms of these, you get back the variance of the function, which was 1 for our balanced function. A second very nice fact is that they are not just orthogonal under this standard space, they are also orthogonal when you define the inner product space according to the edges. In particular, what do I mean is that if you look at the quadratic form of these functions defined over these edges, and you sum them up, you in fact get the quadratic form of the original function. Right? So this is so remember in the log Sobolev inequality we said we lower bounded the quadratic form of a function, and and if we apply that to fj we get these expressions, the quadratic form of the functions fj. And if you sum up these inequalities, we get back the quadratic form we really care about, where f is our original Boolean function. Right? And so far in fact we've not used that the original function was Boolean. The crucial point where we'll use that the original function was Boolean is in order to bound the norms of these functions. And you can bound both the 1 norm and the 2 norm of these functions by measuring the variance along the jth direction. Okay, so this is the only place we use that the function is Boolean. And after with these simple properties of the fj functions, with some case analysis over the log Sobolev inequality, we in fact get our required results. Oh yes, sorry, that's a typo. So that's fj squared is where it's right. So I don't want to. I mean, if you're interested, I can explain some case analysis at the end. I don't want to get into the hairy analysis now. Let me just remind you what the statements are. So what the results are. So we are working over the Cartesian n-fold Cartesian products of graphs. You define the influence of the ith coordinate as the fraction of edges cut along the ith direction. Then we can say that for every Boolean function, for every balanced Boolean function, there in fact exists a coordinate where the influence is large, where the fraction of edges cut along the ith direction is large. It's at least log n by n. And for every Boolean function, there exists another, with small total influence, there exists another Boolean function which is epsilon close, that depends only on very few coordinates, right? And what are the ways we can try to extend this? One important question, I guess, is are there more general product settings where you can obtain these theorems? But maybe something that's more interesting is what about non-product settings? So I didn't get into the details, but there are a couple of very nice results that work in the non-product setting, give you these results. So you have to define influence more carefully, but you can get similar results in non-product settings. Can we obtain any other settings where such results are true? In particular, in fact, for the Junta theorem, we don't really know non-product settings where this is true. It's not even clear in some sense what is the right definition of Junta to use. And for this particular result, I guess one question is, what is alpha g the best constant? In some sense, our result you can as Subhash pointed out, if your original graph was small sized, you could start with just the result for the Q-ary hypercube and then come back to obtain a result of this flavor. But it's not clear which of the two constants gives you a better result. And the question is, what could be the best constant that you can obtain in this case? I think that's all. I will conclude. Thanks. Any questions? Yes, sir.
What is the Cordero-Ruskin and Ledoux theorem?
So that's fairly general. Here are the assumptions they make. They say that the Laplacian of your graph can be decomposed as a sum of Laplacians. So it's sum over Li, and I will define the influence as the quadratic form of Li, right? So that's the ith. The simplest case is when you can assume that L and Li commute. For each I, if you assume L and Li commute, then you obtain these results. Then you obtain the KKL theorem for this, and you again get back the log Sobolev constant of the underlying space. And in particular, it's easy to see that in the Cartesian product case, they commute, and all the previous results they also commute. In the result of Ryan and Carl, they have an assumption that says that Okay, so let me know. They have an assumption which in particular implies that the LIs commute. But you can weaken that assumption a little to say that you can exchange the LIs with a constant loss, let's say, and that also suffices. So that's so it does not assume the product structure, but in some sense assumes this commutativity, which we don't know of too many ways to get around.
And do they justify alpha being the best constant for that context or no?
No. So in some sense, even in the previous proofs, when you use hypercontractivity, it's not clear that's the best you can do. But hypercontractivity gives you back the same constant, the log Sobolev constant.
So in the KKL inequality, there is some sort of in the applications, right? So sparse cut and so on. So you get log n as the integrality gap, which is kind of the log of the number of vertices.
Right.
So using these kind of constructions and your theorem, does it lead to any?
So that's a very good question. In fact, that was sort of our motivation for. So here was an approach to come. So you start with the hypercube. You take orbits over by cyclic permutations. What happens is your expansion goes up, right? And one approach would be that now you take the Cartesian product of that graph, right? And in some sense, if we had the KKL theorem, but with alpha g replaced by the expansion, you would in fact be able to get log squared now, right? And now if you take enough copies, a super constant number of such Cartesian such iterations, then you'll probably improve upon the gap. But the trouble is, in fact, we know that this in particular for that graph, it's not true. So you cannot expect a version of the KKL theorem where the constant is replaced by the conductance of the graph, right? And for the hypercube, there's no difference between the conductance and the log Sobolev constant, so we never realized this. But the log Sobolev constant is in fact bounded by the eigenvalues, which is bounded by the STP value relaxation, which we know is small in that instance. So that doesn't work, right? There's another sense. Okay, so one concrete example, I'll come back to your comment earlier, where we know that we can get better is in fact if you take a hypercube over k square coordinates and you define the influence as now I want to measure the following. So break up the k squared coordinates into k blocks of k each, and I want to define the ith influence as the number of edges cut along the ith block. So there are two ways to getting at a lower bound for this. One would be apply a QRE version of the KKL theorem with Q being 2 to the K here, and then apply the conductance bound in order to get a KKL theorem here. And another thing would be to directly apply a result. And here our result is in fact better by a factor of K. So we get log K by K squared fraction of edges in the ith direction, and if you go via the QRE KKL, you get log K by K cubed as the number fraction of edges. Other questions?
Okay.